All right, I'll take homework if you have it. All right, so I have a few reminders for everybody. First one is there is a seminar today at 2 o'clock if you're able to go. I've had some questions about the Cheminar biology seminar requirements. First, my preference is try and go to one of them because they're good and they're learning. If you go, you write me a paragraph and you email it to me. That's how I know you went. I don't have a sign-in sheet because I can't go to all of them. So if you just summarize it in an email and then send it off to me, that counts as you attending. If you can't attend any of the biology or any of the chemistry ones, I know animal science has a few coming up. They just haven't confirmed their dates yet. That's going to be an option. Or the fourth option is if you have work, sports, whatnot, and you can't go to any of them, email me, tell me your reason, and I will email you back a paper that you then just need to read and summarize. It won't be super long. It'll just be a current topic in science. You just read that and send me a paragraph summary of that. Some good options. Everybody's able to do one of those four options. Okay.
How many do we do?
Seminars in the auditorium, you can do a maximum of 5.
And do you know how many roughly seminars are?
There are 3 seminars for sure, and biology has a seminar every Tuesday at 11.
Okay. So
Sometimes it's students speaking, sometimes it's other people speaking, but every Tuesday at 11, they have something.
We go at least one of any kind of
Yes.
right?
Yep. All right. We'll do. There's no quiz today. We'll do an individual quiz on Monday. Your exam is a week from today. Covers chapters 1 through 4 and as much of 5 as we cover between today and Monday, which will probably just be hemoglobin and myoglobin. And then your chapter 5 homework is due next Friday, the day of the exam. But then there's no homework next week, so it's kind of a trade-off. Questions about any of that? All right. In that case, let's get started with chapter 5. All right, so as we talked about, every protein has a unique 3D structure. And the unique 3D structure allows the protein to perform different functions. So the 3D structure allows the protein to perform a specific function in the body. We're going to, in this chapter, look at 2 globular proteins and then some fibrous proteins at the very end. So we're going to look at myoglobin and hemoglobin as our example of globular proteins that have specific functions in the body. Anyone off the top of their head know what their specific job is? Transport oxygen. And then after that, we're going to look at a few examples of fibrous proteins. And these are going to be things such as collagen and keratin. And the job of a fibrous protein in general, these are some specific examples, is to be structure, to provide a rigid structure for either a cell or your nails or your hair, any of those things. So fibrous proteins are structural proteins. So let's get started talking about myoglobin. I'll work our way up. All right, so myoglobin is a small intercellular protein with a compact shape. Now, as we're looking at the 3D structure of this, we're starting over here. This is labeled protein or amino acid 1 over here. So if that's amino acid 1 at that end, is that the N terminus or the C terminus? N terminus. So here we have the N terminus, and it loops around this way, a little bit of this, that, over here, back around, over here to amino acid 150. And amino acid 150 is the N or the C terminus? C. Excellent. Now, it's a little hard to see in this particular sketch of it. Oh, sorry, 153. I'm reading it wrong. It says 153. Myoglobin has no beta structure, so no beta pleated sheets, no beta anything else. I should say R. All but 32 of its 153 amino acids are part of 8 distinct alpha helices. 1, 2, 3, 4, 5, 6, 7, 8. So those 32 that are not part of the alpha helices, what's their job? To be linkers. I see everybody doing this. Yes, they're linkers. They're either over-the-top linkers or they're hairpin turn linkers. They are going from one alpha helix to the next one, so over here. Now, myoglobin also has this guy right here in the center. Does anyone happen to know off the top of their head what that group's called? Starts with an H, this guy in the middle. The heme. Mm-hmm. And what metal is in a heme group? Iron. So myoglobin has 8 alpha helices, 153 amino acids, and 1 heme group. Let's take a look at that heme group because it has some fascinating chemistry. We're going to spend a lot of time talking about the heme group chemistry. Plus, iron is my favorite metal. It just is. It's just a fun fact. Iron is my favorite element. All right, so heme contains 4 pyrrole rings. So if this is my heme group, can everybody see those 4 pyrrole groups? There's this one, this one, apparently I need a new red marker, and that one. What makes them a pyrrole group? Does anyone remember from the organic chemistry what defines a pyrrole? Has a nitrogen in it. Is a conjugated ring at one of its points is a nitrogen. So all of these have something like that. Now they have some extra things hanging off the sides, which are important, but the main thing is that it has this conjugated nitrogen 5-membered ring. It also contains an iron from your Gen Chem 108. If it's a Roman numeral 2, what does it say about the charge of the iron? Positive 2. So this iron plus 2 atom is at the center and is coordinated between the 4 porphyrin nitrogen atoms here that are part of the ring. And then it also has an interaction with this nitrogen down here. Does anyone recognize this amino acid? The nitrogen-containing amino acid. It has a ring. It's also right here. Histidine. Excellent. Just checking. I'm sure you guys by next Friday will have all those guys memorized. Histidine. Histidines are amino acid that has a porphyrin ring in it. So ignoring the oxygen up here, how many things are coordinated to that iron? How many things are in close proximity? How many things are drawing lines to the iron? 5. 5 right now. 1, 2, 3, 4, 5. Okay. So all the time, iron is coordinated to 5 nitrogen-containing groups. Now, you may be thinking, why do I use the word coordinated rather than bound to? Because everybody in here isn't an inorganic chemist, but it's an inorganic chemistry phrase, meaning that these are not covalent bonds. These are somewhere stronger than ionic, but less than a covalent bond, somewhere in the middle. So it's stuck in there strongly, but you could shake it loose if you really put some effort into it. So coordinated just means stuck in the middle, but not necessarily covalently bound. So if we have a molecule of oxygen entering our picture, oxygen can act reversibly as the sixth ligand. And ligand just means other thing is coordinated to. So again, not a covalent bind, not exactly ionic, somewhere in the middle. Here's my oxygen up here. And it can act as the sixth thing that iron can bind. So you might be thinking, you're probably not, but you could be thinking, why does iron need this many things stuck to it all the time for it to work? Excellent question. So if you just had a single molecule of iron exposed to oxygen, we'll take a little bit of review back to oxidation and reduction chemistry. In this case, oxygen is going to oxidize iron. So what state does it go to if it becomes oxidized? We'll walk back through our memory. Lose electrons, gain electrons. Okay, so if oxygen's oxidizing somebody else, it becomes reduced. So iron has to go to +3. Yes. So oxygen oxidizes this guy, which means it gets reduced, this guy gets oxidized. Oxidized is an increase in oxidation number. So iron goes from 2 to 3. If that happens, we end up in a state that is bad for your body. If your iron +2 gets oxidized to iron +3, iron +3 can't do anything else with oxygen. It can't bind it, it can't get further oxidized. You have an issue. So the same is true if the heme group does not have the protein myoglobin surrounding it. If we just had a heme group floating around in your system, the same thing would happen, that the oxygen would bind to the iron +2, oxidize the iron +3, and then your heme group would then be useless. So the reason we have to have a protein surrounding that heme group is to prevent the permanent oxidation of the iron. and allows for reversible oxygen binding. Why do you want that myoglobin, and by extension hemoglobin, to be able to reversibly bind oxygen? Right, we want it as a transporter. We want it to pick it up in the lungs, take it someplace else and leave it, and then come back and get more. If it wasn't able to do that, if it just picked it up, then your body would starve for lack of oxygen. So we need our myoglobin and hemoglobin to be able to pick it up in one spot, drop it off someplace else, come back and get more. So let's talk about how myoglobin does that. Does everybody have all these notes? Okay. It's going to come back to our old buddy equilibrium. What letter expresses equilibrium? Big K. Big K. Big K. Right, big K is our equilibrium constant. Sounds familiar? Yes, good. Okay. I'll start this. Right, just restating what we just said. The transport of oxygen by myoglobin is reversible. It can be described by an equilibrium constant, a big K. So let's say this is my equation that I'm looking at. Let's take a look at a different few parts of it. What do you think my MB stands for? Myoglobin, right, I'm going to use that as shorthand because myoglobin is a long word to write out. So I'm going to call myoglobin from here on out MB. Here's our oxygen. So myoglobin interacts with some oxygen in your lungs. What is this representing? Right, they're coordinated together, so they're traveling together as a myoglobin-oxygen combo. How about the double arrows? What does that represent? That I'm in equilibrium, that there's sometimes it's going to go one way, sometimes it's going to go the other. And so I can describe this as a K value, an equilibrium constant. What do I put on the top? Products, okay? And then the bottom goes this guy. Sorry, my brackets sometimes leave off the bottom. Right, products over reactants. Would you describe, if I was going left to right, is this an association going on or a dissociation going on? So in your textbook, they're going to call this the dissociation constant. It mathematically describes the release of the oxygen from it. Okay? And everybody remembers what the brackets mean? Concentration. Okay? There's one other mathematical equation we're going to use to describe the proportion of total myoglobin so looking at all the myoglobin in your body, we would like to know at any given time what proportion of that has oxygen bound to it, and it'll vary depending on where you are in the body. That's going to be described as big Y, lowercase, or subscript O2. And in words, that's going to be the fraction of oxygen binding sites that are occupied. And when I say occupied, what does that mean? Has oxygen in it, right? So occupied has oxygen stuck to the heme. Unoccupied means that it's available to bind some oxygen. So mathematically, it's described as all the bound divided by all the possible myoglobin plus all the possible oxygen. So let's think through what this is actually telling us. What if I had a YO2 of 0? What does that tell me about my numerator? It is 0. So if the numerator is 0, YO2 is 0, how much oxygen is bound to my system? 0. I'll write up here. Right, so if YO2 equals 0, there's no oxygen bound because my numerator equals 0. What if my denominator equals 0? What would YO2 equal? Excellent your question. An error. Error on the calculator. Right, you can't have a denominator of 0. Good math skills. Excellent, good review. Okay, what if YO2 equaled 1? What does that tell me about the amount of oxygen bound? It's all bound. All the myoglobins plus oxygens are equal to the numerator, which means all the possible myoglobins all have an oxygen bound. Okay? So all the possible myoglobins in your system all have an oxygen bound to it, which means that your numerator and denominator are equal. What does that mean we can do with this information? Graph it. We can graph it. If anyone had me in Gen Chem, you know my favorite thing in the world to do is graph. Man, I love graphs. I have a real passion for graphs. If there was a job where you could just graph all day, I would totally take that. So here's my graph. Hopefully everyone else in here is as excited as I am about graphs. Does anyone know what kind of graph this kind of shape is? It is also a dissociation curve, binding curve. What shape is that type of curve? Exponential. It's an exponential graph, right? Because it's not a straight line. It's not a sine curve. It's where it starts off steep and then levels off.
Not a parabola because it's not straight enough.
A parabola would be more like this.
Okay, yeah, I just didn't
Right.
think it would be part of
And-
a sideways parabola.
Yeah, no.
Physics, so-
Oh yeah, sorry, not a sideways parabola. This is exponential. Choo, and then flattens off. Exponential. Yeah, parabola would be more like a, and then come back down, and linear would just be straight line.
Okay.
Excellent incorporation of your physics knowledge, though. Good question. I like pulling it all together. I'll make sure I tell your physics professor that you had physics questions. See if that helps. All right, so using our terms of K and YO2, I'm going to rearrange them and combine them. So using our K equation and the YO2 equation, we're going to combine them together to have one equation. We're going to rewrite it one other way. Oxygen is normally found as a solid, liquid, or gas. Good. If it's found as a gas, what is wrong with the way I'm writing it up here? Right, what do brackets mean in terms of units? Concentration. And I don't really have a molarity of gas. I have gas is measured in pressure. So we're going to write it as this. PO2, where the P means pressure, right? It's just a more appropriate way of measuring our oxygen. So let's scoot over here and take a look at our graph. On the y-axis, it looks like I mislabeled it because the y-axis is labeled as y. I actually mean that should be YO2. All right, YO2 is on my y. And then PO2 is on my x. All right, because this is the one you measure. You measure PO2, and then you see how it affects y, your independent and dependent variables. You can come by later if you want to talk more about graphs. We can talk about x and y. So, the amount of O2 bound, which we're calling YO2, so how much bound oxygen is a function of the pressure of the oxygen available to it. And then K is our constant, our dissociation constant, and it's going to define the affinity of O2 for myoglobin. So it's going to define that equilibrium. And for myoglobin, it's a constant. It kind of depends on a bunch of other things that we're going to just ignore. So let's take a look at the graph and see what we can learn about this relationship. If I am at low pressure of oxygen, same down here at 5, that's about YO2 equals a little over 6.6. And remember that, what does 0 mean for YO2? If YO2 equals 0? No oxygen's bound. What does it mean if I'm at 1? Okay. So that's good points to label on your graph. At 0, no O2 bound. At 1, all the oxygen and myoglobins are bound together. So my graph can only go between 0 and 1. So if I am at a low-ish pressure, 5 torr, I'm at 0.6 ratio. What happens if I go to higher pressures, like 25? What happens to my YO2? This isn't tricky. Yeah, it increases, right? What do you think causes that relationship, looking back at your equilibrium constant? It's the name of a guy. Sounds French. It's a little Chatelier's principle, right? So if I increase the concentration of PO2, if I increase this, and I have a constant amount of myoglobin, it has to go this way to go back into equilibrium. If I'm at low O2, it's going to come back this way. So I'll have more unbound myoglobin and more free oxygen. Look at that, pulling it all together. All those different science classes all come back. Le Chatelier's, oxidation reduction. All that time you're sitting through Gen Chem going, when am I ever going to use this? Today. You're going to use it today. I try to let my class know. I was like, if you just wait 2.5 years, about 3 weeks into biochem, you'll need it again. So just make a little star by your notes. We'll come back to it. So then let's take a look at why does myoglobin have this exponential shape to it? Can everybody see if I write? There we go. So the steepness of the hyperbola, the steepness of this part compared to this part, right, in our exponential curve. As the steepness, like this, it's steep through this part and then it levels off at that part. As the steepness increases, as we get to the more steep part of the curve, the value of K decreases. Looking back at your K equation, so K is equal to the concentration of myoglobin and partial pressure of oxygen over the amount bound. So if I have a large amount of myoglobin bound compared to the free, is the numerator or denominator bigger? If I have a lot of it bound, the denominator is bigger. If the denominator is bigger, does this make K smaller, right? The bigger the denominator, the smaller the K. So the more myoglobin oxygen combo I have, the smaller the K is. So the lower the value of K, it's telling you that there's more oxygen bound, that more of the myoglobin has an oxygen bound to it. Let's see. Last thing, looking at this graph, and then we'll move over to hemoglobin. Let's look at two different pressures and then see what it is as YO2. I'll put it up in this top corner. All right, so we'll look at 15 torr and 30 torr and then figure out what the Y values approximately are there. So looking at 15 torr, wait, and if that's 0.9, that's like 0.82. And if I go all the way over to 30, eight, 7-ish, not quite 9. So what does that tell you about myoglobin's ability to bind oxygen if there's a ton of oxygen around? It's kind of flat, right? That the difference between 15 torr and 30 torr, which is doubling the pressure, results in very little difference of oxygen bound. What does that tell you about its ability to release it? If in your lungs it's 30 and in your fingertips it's 15, how well does myoglobin release your oxygen? Not great, not great. So myoglobin is very, very good at binding, but not very good at releasing. So it's very efficient at taking oxygen from your lungs to the rest of your vital organs. It's very good at binding, not good at releasing, which is why it is great for mammals that live under the water. So these are animals that get, like, think of a huge whale, right? Comes up to the surface, takes a big breath, and then swims at really, really low depths for minutes, right? Half an hour, an hour. It eventually gets to a pressure where, right, underwater, the pressure is really, really high, and so it's able to release the oxygen better. So myoglobin is pretty much the main oxygen transporter for whales, seals, other sorts of underwater mammals. And fun fact, people who do that super deep diving with no oxygen, because they're crazy like that, tend to have higher myoglobin levels because they are able to take one breath and travel for a long distance underwater before they have to come back up. So myoglobin is good for oxygen transport if you are mostly an underwater sea creature. I'm guessing most of everyone in here is not a mermaid or merman. I mean, you could be surprised with your pants on and somehow you've like your fin tucked into one leg. But probably you're not, which is why the rest of us use hemoglobin as our transport.
So you double the pressure, but
Yep.
the concentration of oxygen
Doesn't change much. Yep. Yep. So the rest of us use hemoglobin as our main oxygen transporter. So here's my picture of hemoglobin. Sorry, I was thinking about, I have all kinds of fun facts about myoglobin also, because you may be thinking, I'll just tell you some fun facts about myoglobin. So you may be thinking, next time you go to the meat section, why is your meat so red? Excellent. There is hemoglobin and myoglobin in the sliced meats, right? Because obviously it is a muscle that is sliced. I don't know if you want to think about it that way, but that's what it is. It's sliced up muscle. And so in that muscle has myoglobin and hemoglobin. And so the oxygen in there would typically turn, right, because there's no oxygen pumping around in there, it would typically turn all that iron +2, the iron +3. So if you see like the meats that are fresher, they are red, and as they get closer to their due dates, they turn more brown. It's because the iron is going from its +2 state to its +3 state. So it's not going bad, it's just getting oxidized. Sometimes meat manufacturers pump in nitrogen oxide, NO, because that forces the iron +2 to stay in its +2 state, so it stays redder longer. It doesn't mean it's more fresh, it just means it looks fresher longer. There's your fun meat packing fact for later. Or if you're eating barbecue and there's that smoke ring around it, like if you've been cooking brisket for a long time, like there's that kind of pinkish smoke ring that goes around it, that's actually carbon monoxide binding to the iron, causing it to stay pink while the rest of your meat is cooked and turns from iron +2 to +3. I'll tell you, if you want more fun facts, I have a whole sheet of fun facts. So, let's talk for just a few minutes about hemoglobin in our last 5 minutes of class. So, hemoglobin is one of our proteins that has a quaternary structure. It has a quaternary structure because it has 4 polypeptide chains that are in close proximity to each other, like they form one protein of 4 subunits. It happens to have 2 that are the same that we call alpha, and 2 that are different that we call beta. If it has 2 alphas, 2 betas, is that a homopolymer or a hetero? Each of these are homos, like the alphas are homos, but the alpha to betas are heteros. So overall, we're going to call it hetero. Let's see, lost whatever page I was just looking at, my notes, 10.3, 2. Oh, there it is. So these 4 polypeptide chains are going to have extensive interactions amongst themselves. There are 4 areas we're going to look at in particular. One is here in the alpha 1, beta 1 interface. And the other one is over here at the alpha 2, beta 2 interface. Now, it's a little hard to tell from this particular figure, but those alpha beta interfaces, both the 1,1 and the 2,2, are in very, very, very close proximity. And alpha beta interfaces are all hydrophobic. So those are made predominantly of hydrophobic amino acids, which I'm sure if I asked, you guys can name at least 2 or 3 hydrophobic amino acids that are going to be found in there, which might be a great test question. Hint, hint, hint. So, then we have 2 other interfaces that we're going to be looking at. The other 2 are kind of harder to sketch, but I'll do it this way. The interface between either the 2 betas or the 2 alphas. Those are actually solvent-filled channels. Solvent meaning water, typically. So if they are solvent-filled channels, what type of amino acids would I likely find? Hydrophilic and or polar. That should be a big S. Solvent-filled channels, which means they are hydrophilic and or polar amino acids like to be found in there. I will leave you hanging with the question, why use a tetramer? We'll find out on Friday why we use a tetramer. Today is Friday. Monday. We'll find out Monday. Oh, I have to leave you all weekend. Oh, man. All weekend finding out. I don't know how you can always read ahead.
We also learned that bears don't actually hibernate.
Bears don't actually hibernate. All right.